For our first cryo paper, the title is Smart Propellant Tanks, Gauging and Slosh Force Measurement Using Electrical Capacitance Tomography. And the speaker is Andrew Hunt.
Good afternoon, everyone. Thanks for inviting us along. This paper is really about technology that we at Toot have been working on for quite a lot of years, 10, 12 years. But the last 4 or 5 years, we've realized that it has some really strong applications to space propellants. And so we've actually been really this last few years focusing entirely on the space applications, or largely on the space applications. What I want to do today is to just sort of give you a bit of an introduction and bring you up to date with some of the most recent things that we've been doing. So basically the title is Smart Propellant Tanks, and the concept of a smart propellant tank is a tank that knows its own contents. So we talk about gauging and slosh force measurement, and those are, if you like, the two primary things that a tank could know about itself. How much fuel, how much propellant does it have inside the tank? Where is it? How is it moving? And what forces might it be exporting to the structure of the craft or the spacecraft? And so that's what we're going to be talking about today. The technology we use is a thing called electrical capacitance tomography, which has been around for some years. We've taken it into various applications, but in particular, this particular application, we've gone, as you'll see, quite a long way. Hopefully you will have seen the slide change to the second slide. So basically, I've explained what smart tanks are. The intention is to be able to give accurate mass measurement, any fluid, any orientation, any gravity. That's the classic thing that the target that we have, if you like. The data I present here today is for varying orientation, so with an extreme range of orientations, but with gravity vector present at all times in the results that I will show today. So they're very relevant with regard to sloshing and gauging, but when gravity is present. The technology is small, robust and light, enables use in difficult environments, and we measure the mass of fluid, the center of mass and the slosh forces. And we have already tested with many common propellants, including the storables, such as MMH, hydrazine, MON, kerosene. But also we have done a lot of work the last 2 or 3 years, and we're sort of doing live tests at the moment in liquid hydrogen, liquid methane, and various other propellant analogues, including liquid nitrogen. So we've actually explored already quite a range of propellant types, including cryogenics, and it works very well for that all range. They offer different challenges, of course, but we're able to operate across that whole range. So again, in terms of the target, what can we actually do for a spacecraft? We measure the propellant and oxidizer or oxidizer mass, depending on what it is that we're measuring, in real time, in any phase. It can be solid, ice, liquid or gas, in any shape or size of vessel, any orientation, any gravity. And I've already mentioned that we're looking at these other things, center of mass and slosh force. What I haven't mentioned, but is sort of inherent in what I've been saying, is that we're able to measure multi-phase flows. A classic propellant tank, if you like, would have 2 phases. It would have typically a liquid propellant, and then above it a gas propellant, or elsewhere in the tank a gas propellant. But also we are able to measure multi-phase flows in propellant feed flows, through to the turbo pump, for example. If you want to look at entrained gas, that sort of thing, we've done experiments with entrained hydrogen gas in liquid hydrogen with some success. So that's what we're aiming to do. The technology itself, I'm not going to spend a long time talking about technology, but basically we place a set of electrodes around the vessel, and electrodes can be sort of any size and shape, but typically they are plates or plate-like objects which are mounted on or near the wall when we're talking about vessels. And in fact, the tanks that I will show you today, the electrodes have been integrated onto the wall. So they're actually occupying very small, very thin layer on the inside surface of the wall. And what we do is we measure electrical capacitance between those pairs, and then we're generating real-time images. And some of the stuff I'll show you today will be two-dimensional images, where we're actually looking, if you like, at a slice, and that would be the conventional way that we've measured ECT in the flow case, where we take like a slice through the flow. So what you see is a circular image representing the cross section through a pipeline, for example. But more recently, we've moved into doing three-dimensional images in three-dimensional structures. And so I will show you some three-dimensional pictures of fluids inside a spherical tank, for example. As far as we can see, the technology is pretty ideal for space. It's lightweight, it's fast, and by fast I mean that we are able to do the pictures real-time faster than you could see them with your eye. And in fact, we can go as fast as about 4,000 frames a second, which enables us to do some really quite high-speed combustion work. But in propellant tanks, typically, 100 frames a second is typically easily fast enough to see the sloshing, but we can go faster than that if we need to. And as I've mentioned, typical propellants and oxidizers provide excellent performance. They're good fluids, and as are cryogenics. So I'll show you here a sort of simplified screen, I suppose, just showing you some of the interesting things that we can see. So top left of the screen, there's a very simple gauge, and this is showing this tank that we've got here 49% full. Below the gauge there's actually a video in the middle there, which is labeled tank cam. And basically this is some experiments we did very early on, funded by the UK Space Agency. And we were trying one of our pipeline sensors, which we simply clamped around a small cylindrical transparent plastic vessel, half filled it with kerosene, and then used our standard measurements, which are in two planes. So you'll see on the right hand side that there are two sort of orangey blocks showing the liquid, and those are the two planes, if you like, of that short cylindrical tank. And then in the bottom right, there's a sort of a dot, which is actually a dot and a small arrow, and that is showing you where the live center of mass is. And there's a force magnitude just under the gauge, which shows 0.244 newtons, and that is the force being exerted by the liquid on the tank at any time. And if I show you this short video, basically what you expect to see is the force measurement is the blue line spiking up and down. You can see the fluid sloshing about in the orange case in the top right there. And if you also look, if you've had time to see as well, I'll replay that. You can also see the center of mass moving in the bottom there, and the vector of force, which is calculated from the acceleration of the center of mass and the mass of fluid in that volume. So basically, this was a proof of concept that we could measure these things inside a vessel. But in this case, the electrodes were not integrated into the tank. This was, it is a propellant, it's kerosene, so it's a simple propellant, but it's not addressing any of the complex issues associated with making this a measurement in a proper space tank. And so what we've been doing since then, and I'll show you a brief summary of some of the work, is to actually extend that. This system I've just shown you here was 10 centimeters, 4 inches diameter, and about the same length. And we have, both moved up and down in size from there, and I will summarize some of that for you. Just to emphasize that what you saw back there was probably unusual in the fact that the colors of the liquid there was sort of orangey color. Normally we display on a cross section the variations on a color scale from 0 to red, which is 1, where that's concentration of the liquid material, or the higher permittivity material. So most of the images you'll see are actually red when it's liquid and blue when it's gas. We upscaled slightly to 175 millimeter diameter tank, again funded by the UK Space Agency. And you can see on the left of this slide a picture of the spherical tank. You can see the feed-throughs to the coaxial connectors at each end of the tank. And those feed-throughs are packaged around the delivery pipe, so that tank can be connected to a liquid supply or a gas supply. And essentially we tested this on a hexapod system, and we part filled at various levels and then sloshed the tank around and looked at the measurements of what's going on. And really just to show you some examples on the right hand side there, what we're looking at here, if you imagine in this case, this is the tank opened up, and we are looking into the two sides of the tank, and this is the average liquid level within the two halves of the tank. So this is not a 3D picture, but it's a 2D pictures of each half of the tank separately. And what you can see is that at 50 seconds there, 50.645 at the top, all the liquid is in fact in the left-hand side of the tank, but distributed around the tank there on the left-hand side. And at 52 seconds, it's sort of sloshing back and it's coming through the middle, so it's actually in both sides of the tank. And then by the time we get down to 55 seconds there, it's all in the right-hand side of the tank. And if I were to show you a video, I've limited the videos just for sheer size of the presentation, but if I were to show you a video, you'd see those fluids sloshing backwards and forwards. So we scaled up further again, and this was a project funded by Ariane Group and the German Space Agency, DLR, and this was a 1 meter diameter carbon fiber tank. And what you'll see there is it actually was designed very much to check sloshing models, and so it's designed to be a two-dimensional slice of a tank of 1 meter diameter. And so the fluids are designed really to only be in 2D. So that's a short section of cylinder of about 200 millimeters long. And the electrodes are the sort of orangey color rectangles, curved rectangles that you see around the outside. And so we're basically imaging what's going on in the tank. And what you can see there is a typical video image on the bottom left, corresponding to a picture on the top right. And we've published quite a lot of results from those experiments, which is available in papers. If anybody's interested, I can give you details. And basically, this is to show just a simple draining test in this case. So this is non-moving, other than the liquid draining out. And what you'll see is that we're getting pretty good correspondence between the red line, which is our ECT live measurement at 100 frames a second. The red circles are experimental values taken from scales which the system was sitting on and measuring the live weight of the tank. And the blue squares, the flow was stopped, and we took a reference measurement. And you'll see that the agreement's pretty good there. We've more recently been doing work on a back to sort of 175 millimeter diameter tanks, and we've been really trying to improve our calibrations, and I will explain that in a moment in a bit more detail. But essentially what we are able to do here is we're able to part fill this tank. You can see again the connections go to the electrodes through feed throughs in the end of the tank, and basically we're able to rotate this tank to any orientation. And so you can see there that's actually sort of 20 degrees or so pointing downhill, and we are rotating the tank in the other dimension. And so essentially we can rotate in 2 dimensions to get any angle with gravity. Obviously, if this is being done in a normal laboratory, we have gravity present, but it enables us to check the performance of the tank at any angle with that gravity vector. And so what I just wanted to show you is some of the sort of basic outputs. This is not something we normally show people because this is the capacitance output. But I just wanted to show you that what we're dealing with here, we've got 8 electrodes in this tank. We're dealing with a total of 8 independent capacitance pairs. And they vary from numbers around about 20, 30, 40 farads down at the, femtofarads down at the bottom there. So that's 10 to the minus 15 of a farad. Up to 1,000 femtofarads near the top there, a picofarad. And what you'll see is that this is a full 360-degree rotation, and the circles on the lines are at 10-degree intervals. And just to give you a feeling for the way the capacitances change, and what we do is we recreate images of what's in the tank using linear back projection from those capacitances. And what we've done here is we've actually calibrated at 10-degree intervals, and then 10-degree intervals of both dimensions, and then we're able to apply that calibration live to the output of the sensor. And we can apply it live because we have a calibration which is a function orientation of the tank. But the great thing about our tank is we know the orientation because we measure the position of the center of mass. But basically, we can calibrate based on what the angle of the tank is. And then when we come to run the system, we're able to correct the measurement based on the angle of the tank that we have measured from the position of the center of mass. So there's no knowledge of the tank other than what we are measuring. When I show you these calibrated values, the tank is running live, just operating from its own measurements, if you like. We just measure where the fluid is, and then we do some interpretation to create images, which are what I'm showing you here. And then we interpret those images and offer some calibrations in order to end up with the final fill level. So what you can see here is we've got what I've called a first order reconstruction, and this is the high speed linear back projection. That's actually a three-dimensional picture, but I've just got a side view of it with the tank roughly half full. And you can see that, it's showing, obviously this tank is, rotated 90 degrees relative to the gravity vector, or the gravity vector is rotated 90 degrees relative to the tank, whichever way you look at it. And you can see that we'd expect the interface to be dead level across there, and it shows some curvature. That's what I would call a sort of an artifact of the reconstruction. And as I'm sure anybody who's done any imaging work knows that you always get artifacts of various sorts. And then the other dots in the upper half of the tank are telling us that it looks like we've got liquid left in certain recesses in the tank and around certain lines which are within the tank in terms of internal features. And to be honest, we don't know from the outset whether those are artifacts or real fluid. In actual fact, in this particular case, I will take a very strong guess that these are artifacts, that there is no fluid in those locations. But it just shows you that the imaging process does a pretty good job, but it doesn't necessarily give you the precise shape of the liquid you're looking at. But what we're really wanting to know is the center of mass accurate, and is the image useful enough to give you a feeling for what's going on, and is the fill level accurate. And what we can compare that with is what I call ground truth on the right hand side, and knowing the actual fill level and orientation of the tank. Of course, it's a simple geometrical calculation to calculate the ground truth, and so we can compare one of those images with the other. And we've done that with this particular tank now, thousands of angles effectively, and we're able therefore to make a very comprehensive calibration. Just to show you some of these images